Okay, the power factor. Next topic. So we have a current going in at its phase angle and voltage across an impedance at its phase angle. And we go through some identities here, noticing the phase angle of the impedance is equal to the difference. And going back to our formula, the power formula, it's the difference in the phase angle, theta z in other words. Okay, now down here, this graph that popped up, if the voltage is along the x-axis here, then the current leads if it's capacitive, the current lags if it's inductive. The range of angles of the impedance given by this. Range of angles of the impedance. They're never in the second or third quadrant. This is never in the second or third, the difference between the two. For passive components, I should make a qualification there. You could use transistors and op amps and things like that to make something that's in third or fourth, but for passive components, this is what you have. So we can use RMS here instead of this. You can use RMS. So now it's starting to look a lot like the DC case. You don't have to worry about these 1/2 values. This is actually more accurate. If you have we saw a square wave, a triangular wave, different waveforms. If you're getting true RMS, then this will be the true power. This is only true for sinusoidal. So the apparent power is the multiplication of the RMS values, but there's a power factor. This cosine is a power factor. There we go. So your true power that you're consuming, current times voltage times a power factor. And then here's a bunch of stuff. What's lagging and leading, pure inductive. Of course, power is going to be 0 if it's pure inductive, 0 if it's pure capacitive. Power factor is going to be 1 if it's pure resistive, and then it's going to be between 0 and 1 in other cases. So now we got some problems. Here's the power company. You can change this power factor by the total impedance. So we have a voltage supplied, and this is like a line loss. And if you could change the power factor to 0.9, what would be your improvement in power? And that's by impedance matching. You can change the power factor to something like 0.9 using impedance matching. Okay, let's take a look at this analysis, and I'm pretty much going to just follow the slides. I'm not going to do any work on my own just to verify, because it's actually pretty straightforward. There isn't any need to change things. Okay, so first of all, we find the current power factor right here and the angle of the impedance. So, and we use this equation to solve for the I, current. Current, 88 kilowatts right here, divided by 480 volts and the power factor, 0.707. So that's how many amps are being delivered. Now, we can find out how much we're losing right here. These are line losses. And just take this number, square it, multiply it by 0.08 ohms, you get that many kilowatts lost. And so the supplied power is going to be this much. Now, if we can change the power factor to 0.9, we just substitute 0.9 in the equations, like right here. Just substitute it right there. And take a look at it again. So now you run at a lower current, quite a bit lower current. Instead of 260 amps, you got 204 amps. Losses are I squared R, again, same equation, much less loss. You can reduce the line loss. And power companies pay attention to this. They want to really cut those line losses. Let's take a look at the generated voltage. The current lags, it's inductive. Remember power, 480 volts RMS. This is what happens at the telephone pole. And there's lots of transformers around. Lots of inductors, in other words. So we have the power angle, the current lagging it. If you can, the supply, RMS, is, you can just write, this is KVL. This supply voltage is equal to how much voltage is lost through here, which is the current times the resistance, plus whatever the load voltage is, however much is taken by the load. And we want the load voltage to be constant. At our homes, 120. At the circuits outside the homes, 240, and then lines, telephone lines, 480, and it goes up from there. You got several voltages people work with in power. And even if you're a mechanical engineer, don't ignore this stuff, because you're going to deal with motors that are run off these voltages. And motors are inductors and phase angles. And how much power can you couple to a motor? So mechanical engineers, civil, all those people, you deal with motors, things spinning, and they're powered by electricity. Got to figure that out. Okay, so the supply voltage, we can calculate it at the 259.3 amps and 45 degrees, and we can get that number. And if the power factor is 0.9, we have 203 amps at a different phase angle. Did we ever figure out that phase angle? Let's go ahead and pause a moment and do that. So it's pretty easy. I brought up my calculator. You can see my calculator now. It's just the inverse cosine of 0.9. The inverse cosine of this gives you the 25.8. Inverse cosine of 0.707 gives you the 45. Okay, so the current and its magnitude and its phase angle, and then we can get the supply voltage is going to be equaling, it has to equal the sum of the two. The current, let's see, 203 times the 0.08, a very small number, and that takes into account the phase angle, and then the 480 being the load. So we changed the voltage just a hair. The phase angle is, they're closer to in phase. So 26 would be something like this, the negative 25.8, right about there. Okay, gonna stop it here, and now we've gone through an example. I'm gonna have you guys do this one.